So for this second one, we're looking at tangent substitution because this is x squared plus 5, so x squared plus u squared plus a squared is what we're looking at here. So here we'll identify that u is equal to x, again, just like in the last one, and a is equal to, as in the last one, you have to take the square root of that, so a is going to be the square root of 5. And then with that, we've determined what our u is, so we'll want to set that equal to a tangent theta in this case. And then don't forget that you also want dx. So dx is equal to the derivative of this, which is, as we all remember, secant squared theta and d theta. Okay, then if you look at the quantity that's in the parentheses here, that actually is a radical term because of the 2 in the denominator there. It's a square root. So let's see what happens to that. X to the second x squared plus 5 will become, with these substitutions, x is root 5 tan theta, it's squared, plus 5. Squaring the root 5 gives you 5, so you get 5 tan squared theta plus 5. And then notice that you can factor that 5 out. You get 5 times tan squared theta plus 1. And then if you remember your trig identities, tan squared plus 1 is secant squared. So this becomes 5 secant squared theta. So remember that that was raised to the 3/2 power. So what does that tell us? That means that x squared plus 5 to the 3/2 power then must be, since we just said x squared plus 5 is this, must then be 5 secant squared theta to the 3/2 power. And notice what happens here when you raise the power to the power, second power to a 3/2 power. The 2's will cancel and you're just left with 5. That also has to be to the 3/2 power. And again, the 2's cancel, so you're left with secant cubed. Secant cubed theta. Alright, so that's what happens to the denominator. Then for the integral in general, let's see what it turns into. So we got a new integral here, minus 5x. So minus 5, what's x? X is root 5 tan theta, so root 5 tan theta. Then we've got a dx. Let's go ahead and stick that in the numerator. So another root 5 secant squared theta d theta. So that's what the numerator becomes. The denominator, we just went through all of that, and that's what we got, 5 to the 3/2 power secant cubed theta. So this doesn't really look much better, but if we take a look at it, we'll see what is going to cancel. Look what we've got here, secant squared. All of that will cancel here. Secant cubed, we'll get rid of 2 of those, and we'll still be left with 1 secant there. Okay, now look in the numerator here. You got root 5 times root 5. That's 5 times another 5 there. That's going to be 25, or 5 squared. So let's pull these constants out. We're going to get negative 5 squared over 5 to the 3/2. And then what's left inside the integrand here? Tangent in the top, secant in the bottom. So tangent over secant. Okay, let's try to simplify that a little bit. Remember that tangent is sine over cosine, so let's see, tangent over secant, that's going to be sine over cosine, and then there's a secant on the bottom, that's 1 over cosine, so if you got sine over cosine over 1 over cosine, that's the same as sine over cosine multiplied by cosine. So the cosines cancel, and look what you're left with, just sine. Okay, so sine is all we've got left. And then notice in this coefficient here, 5 squared over 5 to the 3 halves. This is why I wanted to write it as 5 squared, because these are the same base now. And you can subtract the exponents to simplify this. 5 squared over 5 to the 3 halves. What are we left with there? 2 minus 3 halves is 1 half. So we're going to have 5 to the 1 half, or root 5. So there's a root 5 in front. And we said earlier that tangent over secant simplifies into sine. And so you see that even after all of this craziness, what do we end up with? Pretty nice integral to do. Antiderivative of sine is negative cosine, so the two negatives will cancel. Root 5 cosine theta as our antiderivative plus some constant. And then we have to remember that we have to also change this back into something in terms of x. So based on what we had up here, x is equal to root 5 tan theta. You need to solve this for theta. You can get, or you can just say tan theta is equal to x over root 5. And then you can draw theta in a triangle. So if you draw theta, what do we know about theta? We know what its tangent is. So tangent is opposite over adjacent. And then the third side by the Pythagorean theorem must be the square root of x squared plus 5. And again, just notice that that's the same thing that was up here. So what we need to do now is change this root 5 cosine theta into something else in terms of x. Well, what is it going to be? We have to look at the theta. What's the cosine? It's root 5 adjacent over hypotenuse. It's going to be root 5 divided by the square root of x squared plus 5. Okay, now look what happens to this. This answer is looking pretty simple if you compare that to what we started with. Root 5 times root 5 is 5, so this is going to simplify to just be 5 divided by the square root of x squared plus 5. Okay, now I put this problem on here just to sort of make a point. If you come back, you see all the work that we did here. If you come back and look at the original problem, and just take another look at it and say, is there an easier way to do this? And if you look at it, in fact there is. Look at the term that's inside the parentheses here. If you say that u is equal to that term, notice what its derivative is. Its derivative is 2x, right? And what do we see up in the top? There's an x there, right? That means this problem can actually be done by regular old substitution. So the point that I wanted to make here is, yes, integration by trig substitution is possible. It is not easy. There's a lot of work involved. But you should always check that there may be an easier way. You could do this with a regular old substitution. You just got to check. So I recommend every time you are doing one of these problems, just ask yourself, can I do this with regular substitution? And if so, then you probably don't want to do this long process of inverse trig substitution, or of regular trig substitution. Let me just show you what that regular substitution would look like. So we'll do that real quick. All you have to do, hopefully we can all do this from what we learned in Cal 1. All you got to do is just say u is equal to x squared plus 5 du is 2x dx. You can then divide this by 2 and get 1 half du is x dx. And then just come up here and change this integral to, let's see, we have a minus 5. We'll just put that in front. The x dx, there's the x, and the dx, they're going to become 1 half du. So in fact, we can just put that 1 half out in front there. And what do we get? Du over u to the 3 halves power. And you can write that as minus 5 halves u to the minus 3 halves power. And then raise that power by 1, power rule, minus 5 over 2 If I raise that by 1, I get negative 1/2, so that's going to turn into negative 2 u to the negative 1/2 power plus some constant. Combine these, the 2's cancel, the negatives cancel, we're just left with 5 u to the negative 1/2 power, which is 5 over u to the 1/2, which is u was x squared plus 5, so that's the square root of x squared plus 5, or x squared plus 5 to the 1/2, which is the same answer that we got in the last way of doing it. And obviously this is much easier. So for future reference, like I said, just make sure and check it. You might be able to do this with regular substitution rather than trig sub.